When I left off last time, I had not shown you how I arrived at the proportional gain required for the lead lag compensator that we placed the zero and the canceling pole for the roll and the pitch axes. I also didn't get into the yaw axis, so I'm going to do those two things real quick. So all this we went over last time, how we determined where we were going to place that lead zero based upon that second pole pair out at A, our motor propeller term that limits the bandwidth of our system and the moment of inertia, of course. And when but I didn't do the gain. So the way I did that was I just established from the initial unity gain Bodie plot the phase hump, the point of maximum phase margin, and grabbed the native, if you will, or plant gain at that frequency, and it was at roughly minus 80 dB, and simply calculated a proportional gain required to bring that up to unity gain. And so there is the proportional gain required to give us unity gain crossover here, unity gain crossover at our frequency of maximum phase margin given where we place that lead zero. And another way to look at it in the root locus is here I just ran a root locus up to that gain value, and the pole pair then ends up here, and so we placed our poles in the left half plane. And if you think in a textbook, whether it's a second order system, you can think of this as damping ratio, percent overshoot, phase margin. It's related to this angle between the y-axis and that pole there. So this angle right in here. So we can expect to get something like a second order response, again just from that dominant pole pair there. Now the yaw axis model is structurally the same, only the plant gain is different because of the drag factor and a different moment of inertia for about the z-axis, where we have all four motors on massless rods, and so our body moment of inertia is this, and we've got the drag term instead of the drag factor instead of the thrust factor in the numerator, and we come up with so we have a different plant gain, and therefore same process for determining the plant gain at that point of maximum phase margin, and from there determine a proportional gain value for the yaw axis, and that's this rather large number here. And we come up with a Bodie plot that looks identical, unity gain crossover at the point of maximum phase margin. And again, it's the same frequency because that lead zero is limited by this second pole out at A in the same manner as the other axes. So that's how we picked our proportional gain term for the roll and pitch axes, and also for the yaw axis. So what I'm going to do next is divert into a simplified model and simulation of the basic double integrator plant, the satellite attitude control problem that you'll find in a controls textbook, and then we'll jump back into this. It's going to be really behaviorally similar, but just not as complicated by these other terms. So I want to show some simulation tools, and then we'll get back to our quad rotor.